In this episode, we're going to look at Infection, a PHP mutation testing framework. Hi, I'm Mark Bradley, and welcome to Testing All the Things, a screencast in which we use live coding to demonstrate different types of testing tools and techniques. In the previous videos, we have achieved 100% line code coverage by following strict test-driven development. But how can we be confident we've covered everything, that we haven't got missing tests or bugs in our tests? This is where mutation testing can help. A mutation testing framework makes small modifications or mutations to the code under test. It then runs the tests and looks for failing tests. If no tests fail, then the mutation or modification has escaped and you've got a bug in your testing. Let's look at the code. In this video, we're not going to spend too much time writing any code. I have already created a couple of examples that we will look at in a moment. But first, before we started, I set up Infection and set up this Infection JSON configuration file. Setting a timeout, the directory where it will find the source, where to output the logs, and what mutators to run. Now that we've looked at how Infection is configured, let's look at some of the code. So the first example we're going to look at is the myString test and its implementation. So if we open that up and split them so we can see both at the same time, we can see that myString has at the moment a single function which is to uppercase. The idea of the function is it will return an uppercase version of the string given to the object during construction. If we now run the tests and look at the code coverage, we can see that the myString class has 100% line code coverage, and this is really good. However, let's go and look more closely at the code. First of all, if we look at the test on the left-hand side, we can see that there is a bug in the assertion. We can see that we're asserting that the expected and the actual are coming from the same variable. So we've already got a bug here in our test. But our test passed because of this bug. And if we actually go over and look at the implementation, there's a bug in the implementation too, because of a simple typo or mishit of the keyboard when kind of choosing what function to use in the IDE has actually meant we're using the string to lower function rather than the string to upper function. So let's look at how mutation testing can highlight this problem. So if we look at mutating the myString function, we run that. There we go. So if we look at the output here, we can see that one mutation was killed, but another one escaped. To understand the bug we have a little bit better, we can now go and look at the log file created by Infection during the test run. So this is the Infection log here. So if we open it, we can see that when it stripped back the function string to lower and just returned the value, the test still passed. So we know we need to go and look at the test around this and also the implementation of this. Let's go and have a look now. We know one quick fix is to change the expected here to be the actual, so let's do that. Okay. And if we save that, and now we can run our test again, we can see that the test actually is now failing again. We're expecting Mark in uppercase, but we're actually getting Mark in lowercase. So it looks like now there's a bug in our implementation, which has been highlighted. So if we change this to string to upper, okay, save it, and we'll rerun our test. Okay, so everything is now passing, which is good. We should still have 100% code coverage because we haven't really changed anything. Yep, still 100% line code coverage, which is good. And if we now run the mutation testing over this class again, there we go. So we now have killed both mutations, and we now have no bugs in our test and no bugs in our code. This was quite a simple example. It was very easy to see that bug without mutation testing. I have seen cases in testing where people have made assertions on the mock objects rather than the objects returned from the code under the test. This was very hard to spot just by looking at the code by eye, but mutation testing kind of highlighted this problem quickly. So this is all we're going to look at in this example. This now is complete. Let's move on and look at the other example. So if we close all the files, and now we're going to open up the integer test and its implementation. Let's move the implementation over to the right so we can see it. And get rid of this, and just have a look now. So we have a very simple integer class. On construction, it takes an integer value, which it holds, and then we can have one function that we can use, which is the greater than function. This takes another instance of an integer and tells us whether the value of the given one is greater than the one contained in our current object. And we have some quite good tests here now. So we have a test that 5 is greater than 4, and we have a test that 4 is not greater than 5. So if we run this, and we'll run it with code coverage again to see what happens. There we go. Okay. And now, as we can see here, we have 100% line code coverage again of our integer class, which is excellent. And if we look at the implementation looks really good. It's very simple. It just checks that the value of the current object is greater than the value of the given object. And the tests also look really well set up. We've got two integer objects here, 4 and 5, with the values 4 and 5, and we check that 5 is greater than 4, and we check that 4 is not greater than 5. So, what can mutation testing show us in this case? So if we run the mutation testing for the integer, run it, there we go. Okay, there we go. Okay. So here we can see that we have killed 2 of the mutations, but we still have an escaping mutation. So let's look at what happens in this case. If we look at the infection log, we can see that when the mutation is swapping the greater than symbol for greater than or equal to, our tests still pass, which means we have either we're missing a test or our implementation is not good. So how can we rectify this? Well, it seems that our function is called greater than and not greater than or equal to. So it appears our implementation is correct, but maybe we're missing a test, and we can solidify our testing of this function with one additional test. And this is a very simple test to add. We can check that, new test, test that 4 not greater than 4. If we take 4, put it here, and then we can do this, assert false, that $4 greater than $4. There we go. Okay, so if we run our tests are all green, and this wouldn't have affected our code coverage anyway because we have just continued to test the same function and the same line of logic within that function. So our line coverage should, we'll just double check, be at 100% still. Yep, still 100% line code coverage there. So that's really good. Now let's rerun our mutation testing on the integer class. look at that. Excellent. All of the 3 mutants were now killed, and our integer class is fully tested, and it shows us now that it's going to be almost impossible to put a bug into this function. We test all of the potential cases that occur. So far in this video, we've only looked at the logging that infection creates for a more detailed look at what is going on in our code, because we're only looking at very small examples. But when we're looking at a bigger project, we need a way to know the quality of our code, to check that the quality of our tests is being maintained as we add functionality to the bigger code base. And for this, we can look at the output metrics here. We have mutation score indicator, or MSI, the mutation code coverage, and the covered code mutation score indicator. But what do these mean? First of all, let's take out this test so we can see them go back to a different number than 100% across the board. And then we'll rerun our mutation testing. There we go. So we now have differing percentages for the MSI and the code covered MSI. But what do these mean? Let's first look at the mutation score indicator. To show you how these numbers are calculated, we'll write this in some pseudocode. If we take the total, so we want to take the total defeated, and this is all killed mutations plus all the timed out mutations plus any errored mutations. To calculate the percentage, what we do is we take the total defeated and divide it by the number of mutations, so total mutations that were run, and we just times that by 100. So that gives us our MSI, like so. That was a nice simple one. The next number we can look at is the mutation code coverage. Now this should be the same as your line code coverage, and as we can see here it's 100%, and it was 100% in our test. But to calculate this, first of all, you want to take the total covered by test mutation, which is calculated by the total mutants count minus the not covered by test. Turn it up a bit. We can get rid of this now. There we go. And then the calculation for our mutation code coverage, let's call this MCC, is we take the total covered by mutation tests, and we divide that by the total mutant count. We'll call it total mutation. There we are. 10 times by 100. Okay. And then the final number is the covered code mutation score indicator. This is the MSI for code that is covered by tests. So this disregards any code that you've got that's not yet covered by tests. This is calculated by, so we'll do this again, so CCMSI is the total defeated with the typo divided by the total covered by mutation test and times by 100. There we go, right. Let me fix my typo. There we go. When you're looking at a larger project, you want to look first of all at your mutation score indicator. This is the key metric to look at to understand the quality of your code coverage and the quality of your tests. The lower this number is, the lower quality of your tests, the more you're missing, the more tests you're potentially missing, the more bugs you're potentially missing in your code. Whilst I was showing you the examples of mutation testing, I was using some make targets that just ran the mutation testing over single classes at a time. When you're testing your own code, you want to be running your mutation testing over your entire code base. But mutation testing is a slower form of testing, so you don't want to be running this as part of your normal kind of TDD cycle. You might want to run this kind of towards the end of implementing a function or a class, but definitely not every time you make a small change to any code. One of the things I do use in projects at work and on personal projects is I add a little make target that allows me to just run mutation testing over any modified code. This is a good way to show me any kind of refactoring I could do or any improvements to the test I can do. On the project I'm on, we follow kind of the Boy Scout rule, so we kind of try to leave the code base cleaner than we found it. And a great way to leave the code base in a better condition than you found it is to add tests that might have been missed during the original implementation. And this is a great way to show you where you could maybe improve a class or some testing as you're editing that class. As with line code coverage, you could use the mutation score indicator as a blocker on your pipeline. If your MSI number goes below a certain percentage during testing, then you might want to reject that change to the code bases and to allow the quality of your code and your testing to always increase as you add new functionality to your project. That is all of the demonstration of mutation testing I wanted to do today. We will continue to use mutation testing in upcoming videos to continue to ensure we're writing all the tests we need to. Thank you for watching this episode of Testing All the Things. I hope you found it useful. If you enjoyed it, please rate the video and subscribe to the channel. If you did not, please leave constructive feedback in the comments. If you would like to suggest something you would like covered in a future episode, please leave a comment as well. I'm Mark Bradley. You can follow me on Twitter at Braddle, or if you're just interested in all things testing, then follow at TestingAllThe.